The greatest story never told is the story of our planet.
We're going to telescope out into possibly one of the most profound lessons that we could take away from Synapse, and this is the story of carbon. You know, we're talking about fossil fuels and energy transitions and technologies which are guzzling the energy resources of the planet. We've talked about every aspect of our collective lives. We haven't looked at the molecule that makes all of us, our material reality, our cosmic reality, our individual realities, who we are. It's the absolute building block. And there is a deep time history of that as well. It just blew my mind. I'm so excited to share this session with you. It's a presentation by a brilliant mind in search of a home. Pranay Lal, he's a geologist, he's a biochemist. He's written a fantastic book called Indica. I would urge all of you to go out and buy it. It is about the geological history of India, climate as a sculptor, climate as history, climate as politics. So do go out. It's a mind-blowing book. It's about dinosaurs in the Deccan, lava in Ellora, jellyfish in Jodhpur. It's a thriller. He's also written a book on the virus. It's just out. You know, it's his new book on the history of viruses. So fascinating work. But here's the irony. He is this brilliant mind, not attached to a university or a home. He's in search of it. There's universities here. There are, you know, school owners, educators. He belongs to the classroom. So I'm here personally making a pitch for Pranay Lal. Ladies and gentlemen, please welcome him on stage.
The greatest story never told is the story of our planet. To me, I think this is a story that we should have been told when we were children. It's a story that is 4.56 billion years old. 4.56 billion years old ago, the orbits of the universe, of our solar system, were yet to form. The planets and the planetary bodies were yet to find the space in which they would take a regular orbit. In these irregular orbits, there was a moment when two bodies collided and created a massive firework that would actually go back and, you know, create a massive amount of spill of rocks and liquid rock. The amount of energy was immense. What would happen would be that there would be two more planets that would form again. One would be the proto-Earth, the other would be our moon, our satellite. Now, this moment in history is perhaps the most important because at this time on Earth, we get the core, the mantle, and the crust. The core is the place where all the energy of the Earth is stored. It gives us energy from the inside. Most planets, most satellites, like our moon, don't have it. What this core does is not only gives us gravity, but also drives the energy which creates landforms and landscapes and the oceans that exist today. The other thing it does is that it holds everything that is around it in the form of the atmosphere. The moon, which looks dull and gray, actually had a live core when it was formed 4.56 billion years ago. But it gradually lost that energy, and it became quite lifeless as we see it today. But if you look at all the pockmarks that it has, it's actually protected the Earth from all those collisions that happened several times on it, taking all those injuries on itself. But Earth also was severely assaulted by meteors and asteroids. Now, this is the moment when all the water that we have on our planet started to form. We also got diamonds, we got gold, we got platinum. So this amount of energy that was coming in from outside was also feeding in minerals. These minerals are critical for us because they are the ones that will shape a lot of future metals, metalloids, and other compounds that we take for granted today, including lithium. At the same time, the volcanoes were very active. Remember, the core starts to shrink. The mantle, the middle layer, also produces a lot of energy, and it comes out in the form of these large volcanoes that are spewing out a lot of lava and gases. Now, this is the second phase when all the water also gets created. Now, this is an important phase in our planet's history because this causes the reworking of the crust, and new amounts of minerals get cooked and recooked and born again and again. This is a rock which is not too far from here. If you go from Gurgaon to Faridabad, it's on a cross-section of a road. Look at how beautiful this is. It looks like if there are students here who've studied chemistry, and I know there are a couple of young children there, it resembles like a filter paper on which we used to play. You put a dye in the center, you put more dyes in the center, put alcohol, put water, and it starts to spread, right? And that's the beauty of it. That's what minerals do naturally, right? Now, this is exactly what happens in nature. There's a process of creative destruction and creation happening throughout, and we don't see it. We consider rocks to be inert. They are not, because they're constantly working and reworking with microbes. They're creating soils. They're breaking down. Our eyes don't perceive it, but this is something which is happening on a daily basis. This may look like a rock to you. It is. It is actually a fossil. Notice the center. It's got concentric rings. This is actually a fossil among the oldest in the world called a stromatolite. Stromatolites were basically microbes that worked in partnership to create these colonies. So they look like large onions. This perhaps would be tens of thousands of years old. They take a year to grow a circle around themselves, and they girdle like tree rings or coral rings. They grow around each other. Why is this creature important? Because from 3.5 billion years to 750 million years, this was the creature that produced all the oxygen that you and I breathe. All the oxygen that was created was made by these guys, no one else. Okay? Now, this particular specimen is from a place called Sonbhadra. This rock is extinct because it was used to make the toothpaste that you and I used to use in the 70s or 80s or 90s. After that, this rock is gone. So rocks also go extinct. We extract so much rock from our landscapes that it's gone. So your Kota stone that you see in your kitchen counters, well, it's almost gone, right? So rocks are also getting extinct, but the beauty of this rock, like I said, organisms that came together in very hostile conditions when the earth was very hot, very toxic, very warm, very limited water. These creatures came together to produce the first synthetic organisms using diverse minerals that were there to produce oxygen. And this is what it is now. We do produce minerals. Nature by itself produces a lot of minerals, but the largest producer of minerals is us. Since World War II, we've been adding 20,000 or more chemicals into our environment, for which microbes and other creatures don't know what to do. They can't digest them, they can't assimilate them, they can't break them down. So that's the problem, because we have an accumulation of waste like this for which microbes have no answer. These synthetic chemicals are something that is a challenge because it's breaking down ecosystems, not because plants and microbes are not able to take them over. It's because microbes and plants and other creatures cannot evolve that fast. What I've just told you is basically something that was summarized by Robert Hazen. What he said was that there are clearly 4 major cycles in which minerals evolved. The first, if you recall, when the planets collided, we had roughly 350 minerals, just about that much. But then when the volcanoes started to come up and, put, more heat and more minerals from below, they started to recook the surface, and we have 1,500 minerals. When you look at the arrival of the microbes, 3.5 billion years to 750 million years, these creatures produced all the oxygen that you and I breathe. They created oxides and carbonates and silicates and all those beautiful minerals that you and I use in our daily lives. And finally, this is the era when we see the chemicals that you and I use, which are a problem because they are accumulating and we don't know what to do with them. I'm going to take a minute to tell you why the history of carbon is important and why we need to look at it from a deep time perspective. Now, carbon is among the many minerals, one of the compounds that works with several minerals. It has this ability to combine. It's a very, very prolific element that can combine with several other chemicals to make complex creatures. Now, the first thing that I want to show to you is this image. This is from roughly 260 to 255 million years ago. Imagine this to be Andhra Pradesh because we find fossils of these creatures here. Now, the creature that you see on top, that tall plant, that weird-looking plant, is actually the ancestor of the moss, the thing that you see lining on walls or in moist swimming pools or places where, it's kind of slippery. Those tiny things that carpet the floor or the walls, this plant was about 40 feet high, and it has now become that small. That's adaptation, that's survival, but it survives, right? The creatures below, these plants below, are cycads and palms. You see cycads and palms even today in our gardens. Nothing spectacular, they've stayed the same by and large since the time they emerged. I want you to focus at the bottom of this painting. There is water. This is the period where a lot of water used to flush the land and carry this vegetation into shallow basins. And in these basins, when the accumulation of biomass would happen at a frequent level, this would create all the coal and all the oil that exists in the world, at least in the southern hemisphere. In the northern hemisphere, it happened in a different age, about 400 million years ago, in an era called the Carboniferous. This era is called the Permian Age. Our coal, the one found in Australia and like I said, in the southern continents, is from the 250 million year old. Now, why is this important? Because plants, when they are buried deep and they're put into shallow basins, they do not decompose as fast or release carbon dioxide back. They need to go back into the basins, decompose, and stay there. That's the reason why we have fossil fuels. They're called fossil fuels because they are actually fossils which were made from these kind of plants, right? Now, the trick here is to look at plants in a way, in a holistic manner. I want to come to that point a little later because I want to tell you why carbon, which stays on the surface. Now, I don't have a pointer, but if you were to look at where it's written terrestrial biosphere, that's the place where you have forests. That's the place where you have all the vegetation. Now, in deep time, when the floods would happen, they would take the biomass to that juncture where you see where it's written subduction zone. That's the place where all the the biomass would go and accumulate and create the oils and the coal and the lignite and the anthracite, all those fossil fuels that we use. The challenge here is that the carbon that we collect now, we take it from coal mines and from oil, use it within weeks, release it in the air. What took millions of years to make is just taken out in a jiffy, burnt and thrown out, right? We are not putting back the carbon that we are capturing in whatever little way that we do to put it back into this cycle. That cycle is broken. So if you were to look at from the deep time perspective, our carbon cycle is broken because we are taking out far too much from the coal reserves and the oil reserves without putting back anything else in it. I want to talk to you about how humans have been interfering with the climate processes. Now, this is just a single slide just to tell you about the human stain, how deeply we've impacted the land and the oceans. Now, if you were to look at the dark brown parts, look at how dark it is over India, eastern China. You look at America, a recently colonized country. If you look at it in terms of human history, it's very recent that Canada and America were colonized, right? But look at the dark color that is there. Of course, we expect Europe to be dark because that's still soil that has been tilled and worked and overworked, just as India has been. But look at the seas as well. The dark blue color that you see, especially over Australia, right here. It's a recently colonized continent, but the sea life, the marine life, the overfishing has already depleted these places. So many of these places that you expect that marine lives would be secure. For example, the southern oceans here of West Africa, these have been compromised severely because of overfishing or because of industrialized fishing. And of course, the land that has been worked. So our soils have become thin, the rocks have got exposed, we don't have the soil to work on, right? That's the first point. The second point that's before us is that the acidification of the oceans is a very, very major challenge for us. I want to give 3 propositions to you, and I'm going to give you these propositions from India, from our subcontinent, because I think it is more relatable. My first story is going to be about the Kumbh Mela and the river Ganga. I'm going to proposition this, that we've all heard this from our dada dadis and nana nanis, that Ganga ka pani kabhi kharab nahi hota hai, right? You've heard this. The water of the Ganges never gets spoiled, right? Now, why is that the case? And that is a fact. It is a fact. You take the waters of all other rivers and put them aside, including Brahmaputra, the water of the Brahmaputra will decompose roughly at the same rate as other rivers. But the Ganges water, no matter how long you keep it, it's going to stay undecomposed, unpolluted, unspoiled. And here's why. A man called Harold Urey, who perhaps was looking out of his window, I can't recall whether he was at Columbia or was it in New York University, but he wrote this majestic book in which he imagined that there was a geologic cycle happening somewhere in the world in which rain, when rain falls, it becomes dilute carbonic acid. It's like your Coke, okay? Coke has too much concentration of carbon dioxide, but if you were to look at the rainwater, as it descends, it captures carbon dioxide and becomes a weak acid. And when that weak acid falls over the young granite rock in western and central Himalaya, it etches out something called calcium silicate. Now, when the calcium silicate, I know a lot of you hate chemistry, I know. I'm sorry, I'm imposing this on a Sunday morning. Apologies. But what I'm trying to show here is that it would latch onto the calcium, release a ligand called silicon oxide. Now, this is the one that actually keeps the water sterile, nearly sterile. There will be other creatures, but they will not decompose. They won't create an organic mess in the bottle. Now, as this water goes down, as the Ganga flows, it carries that additional carbon, and takes it down the Bay of Bengal through the delta into the Bay of Bengal. Now, this remarkable process of carbon capture happens only in the Ganga and no other river. This is why Ganga is a river that needs to be protected, not because it's religious and mythical and legendary and so pious to us. It's because it's a global common and it is doing a service about which we don't even know, right? This is what the Ganga's mouth looks like in summers. It's taking out so much sediment. If you were to put the sediments of all the rivers in the world on a map, this is how it would look like. Look at how much Ganga, Brahmaputra, Teesta, Meghna, Jamuna, Arial Khan. There are 800 rivers in the Bay of Bengal that drain into the Bay of Bengal from the mouth of what is between Bangladesh and India. 800 rivers and rivulets and tributaries, okay? And look at the spread of the sediment. It goes well beyond the Andamans. That's the power of the Ganga. It has created submarine canyons that are deeper than the Grand Canyon. In fact, one of the places, the last places on the Earth, on our planet, where we don't even have a map of the seafloor of any place is the Bay of Bengal, because we can't. It is so thickly deposited with the sediment, and this sediment is the one that has captured all the carbon, organic and inorganic, right? That's the beauty of the Ganga, the Brahmaputra to some extent, and the Meghna and the Jamuna. Now, for that reason alone, 22% of the world's biogeochemical carbon capture happens in the Ganga. It's a fact that we don't even know and we don't appreciate. Okay? Now this is, we shouldn't clap because this is getting compromised. We've got dams which stop the sediment. We've cleared the fields, the forests are gone, the grasslands that were there are gone. Right? Now that's the problem, because there is no process, there is no organic carbon that is going into it, and even if it goes, there are dams that stop it. So the silt, the sediment that is supposed to flow into the Ganga is getting compromised. The Indus was a very powerful river. Until 4 million years ago, it was more powerful than the Ganga and the Brahmaputra combined. And it would send in a lot of sediments even then. The problem is we've started more recently, of course, post-independence, damming the rivers all along the Beas, the Satluj, the Jhelum, the Indus. All of those are getting dammed, and the sediments are not reaching where they should be, into the sea, right? There are places in Pakistan where you can cross without even wetting your toes because the Indus dries in the summer. Thankfully, it doesn't happen to Brahmaputra, and thankfully, it doesn't happen to Yamuna or to Ganga. But the day is not far when our damming is going to be doing that. Let me come to my next proposition, because this is going to blow your mind. When somebody told me this story, I didn't believe that person. We didn't have deserts that we know. Look at the Sahara, it's a green paradise. This is 55 million years ago, the time when all the great mammals were evolving. You know, our ancestor was, the earliest ape was not even in the scene, but you know, the great giraffes, the great rhinos, the horses, their ancestors were coming there. And if you notice, India has yet to collide with Eurasia. It's not that India is colliding, it's because the sea in the Indian Ocean, the volcanoes under the Indian Ocean are the ones that are separating the seafloor. And that's the one that is pushing the land. It is not that the land is migrating, it's the sea that is expanding, okay? Now, it's going to create the largest mountain chain, which we know as Himalayas. It's going to raise Tibet. And when it does that, it will start first by creating a permanent ice cover here. So Antarctica gets its permanent ice cover roughly 18 million years ago. Arctic is yet to form, right? But notice that the deserts exist in Greenland, in west margins of America. There's no Sahara, there's no Arabian desert. There is a desert in China, which is large. Nothing in Australia. Now, if you put them all together, if you come to 21,000 years ago, you start seeing the emergence of the deserts. You start seeing specks along the Saharan desert from the center. The oldest part of the desert is perhaps in Chad, right? You start seeing that in Iran and south parts of Afghanistan, there is some aridity that is arising. And what is also happening is that the Kalahari, which was expansive, it becomes a very, very large desert. It shrinks later. We know that, right? But look at it again. You don't have a Simpsons Desert or the Great Australian Desert yet. We don't have it. We don't even have a Thar Desert yet. So the deserts are a recent invention. They are a recent creation of the natural world. Now, let me show you this image. It blew my mind when I first saw it. I wish the lights were off, but nevertheless, it's a beautiful piece of graphic. What you're seeing here is the western part of the western half of Sahara is leaching out its dust, and it's moving across the Atlantic, over the Amazon, into the Caribbean islands and South Florida. And this is what fertilizes the oceans, the Amazon, and the Florida Everglades. Without this, the tropical flowers, the tropical flowering trees, the great Amazonian forest would be dead. Why? Because it rains so much in the rainforests that it just does not hold that much minerals. The soil has been leaking out, and also these are rocks called, the soils that are formed there are called laterites. They're very poor in minerals. So you need this additional dose of iron, of phosphorus, and potassium, which you get from this desert dust. And you don't have this in any other place. So these kind of massive clouds that carry dust across continents are the ones that actually make forests like the Amazon possible. Let's look at India. This is a post-monsoon image which actually shows dust being carried into India. So the forests south of the Dangs, Panchmahal district, to Kerala, actually benefit from the dust that comes from East Africa and the Saudi Arabian desert. And if you were to look at other deserts, the Gobi Desert fertilizes another set of ecosystems. The Andes gets its share of dust from another. So you have this huge metabolism of dust, this massive engine in which dust is actually creating a process of fertilizing forests across the world. And something that you and I take for granted, that the forests exist and therefore they live by themselves. That's not true. They depend on nourishment that comes from other places. I'm just going to close with my third proposition, which is this. We imagine that trees are the ones that provide us all the free oxygen. Everybody thinks that, if I plant 100 trees next to my garden or in my yard, I'm getting free oxygen, I'm getting, very good. It's a good feeling. I mean, of course, they respire and they give you that consolation, that solace that, you're getting that. But that's not true, because the next day, if you were to create a budget, the tree would be consuming that oxygen the next day, right? So it's not putting any additional oxygen, which is free, right? You get the point? Basically, what it's going to produce today, it's going to consume tomorrow, and it's going to do the same thing the next day and the next day. It's only going to grow. In fact, when the plant grows for the first time, it's actually depending on the oxygen that somebody else has produced, right? So we are looking for what is the creature that produces all the oxygen which is selfless, free, and in large quantities. And that happens in the seas, and in the rivers, and in the ponds. This is in Bandhavgarh. I don't know how many of you have seen it. It's a beautiful 110 feet long reclining Vishnu. I love this sculpture, don't get me wrong, but what I'm interested in is on the left, what we in North India call kai, right? Or in English we call it slime, or there are even dirtier words if you go to other languages. They're just not complementary. But it is this slime, this grime, this top layer of gunk that is there, is the one that produces all the free oxygen that you and I breathe today. Other than that, that was made by the stromatolite. Remember the fossil I showed you? This guy? Well, this guy produced it for us. It's now extinct. It's available in some countries, tiny pockets in in Australia and the Caribbean islands where it's got a bit of a sanctuary. But this creature is by and large extinct. What's producing all the free oxygen are these guys. Now imagine, till 1988, we did not know the most amount of oxygen or the largest carbon capturing creature was not even known to science. It was accidentally discovered. And it is perhaps the most abundant creature which exists in our lives, but we never saw it, right? Now this is called Prochlorococcus. Pro means first, chloro means green, coccus means round-celled creatures, right? Now Prochlorococcus and its cousin Synechococcus together release 28% of the world's oxygen that you and I breathe, 28%. And they were not even known to science till 1988 when the paper was written saying that this is the biggest photosynthetic engine in the world. Until now, if you were to even talk to a biologist and ask them which is the plant or the tree or the forest that produces most oxygen and captures the most carbon dioxide, they would all say this forest or these trees. They would not talk about these microbes that live in the oceans and the seas. So our misconception, we are terrestrially biased. We love to think about land, we don't like to think about ocean. Remember, 78% of the planet is actually water, right? Just want to show you, okay, this is the other hero. Trichodesmium, it regulates all the nitrogen in the world. Other than the legumes that do it on the land, this is the Amitabh Bachchan of nitrogens. And this guy is tiny, but a very, very powerful organism that looks at managing the phosphorus cycle. But if you were to keep your terrestrial bias away and you want to look at oceans and land in an objective manner, you'd see that the photosynthesis that happens all over the world, it's largely concentrated in the seas. This is the depth of the color is actually telling you how strong the photosynthesis is happening. That means carbon capture is happening and oxygen is getting released. Now the reason why microbes are better than trees is because they have a very tiny life cycle. They grow quickly, they multiply rapidly, and they die instantly. So they produce the oxygen, and when they die in the oceans or the rivers or the lakes, they go and sink at the bottom, right? This is what we want. We want the carbon to go back down into the depths, not stay on the surface. If carbon stays on the surface, like you saw in the Californian wildfires or the wildfires that happen in Canada, our forests will catch fire instantly, right? Or they start decomposing. There's a leaf fall, it will start decomposing. So forests, by and large, are not a sink of carbon, they're a source of carbon, unless they are better managed, right? Now, these organisms, and I speak for organisms and minerals here, is the fact that all the carbon that gets captured in a day's time in the 80 meters where these organisms are most active, they capture it, they release the oxygen, die, and sink. That's it. It's a simple cycle, and it happens day in and day out. It's a no-brainer when it comes to carbon capture that organisms are far better than trees. So I just want to close with these two beautiful images. The smallest vertebrate in the world is a collection of these fluorescent, bioluminescent fish called the lanternfish. And there's an immense variety of them. I've just given you a snapshot from the Indian Ocean. But it's not just the smallest creatures that eat these small planktonic creatures, these microscopic creatures that float on the ocean surface that are capturing all the carbon, producing all the photosynthesis. But it's also the whales. So from the smallest creature to the grandest creature that Earth has ever seen, everybody depends on these photosynthetic creatures. These tiny creatures that were not discovered till the mid-80s or early 90s, we did not even know they existed, right? Think about it, how little we know about science and how little we know about the climate process. And if I were to combine my three stories of rivers, the Sahara dust or the desert dust, and the oceans, this is how it looks. The metabolism of how the dust feeds into the oceans, and how the rivers are providing nutrients to create a huge network in which there's nutrient that is entering into oceans and there's burial happening right there. The operative word for everyone here should be, how much carbon are you burying? It's not how much carbon you can capture. Carbon capture is simple. How much carbon can you bury, right? Okay, I'm just going to make 4 last points. I don't know, I think my organizers might be pretty livid that I've taken far too much time, but I guess climate change, that's my time, right? So I guess I'm okay. So to my sense, speaking from behalf of microbes and minerals, the current climate protocol, the way it's been designed, is pretty half-baked. And I don't think this is something that is going to actually bode us well in the future. Because oceans, seas, rivers, lakes, ponds don't feature in the current climate paradigm, right? And I think if you really want to make a difference, you should be thinking about how you want to look at microbes and minerals, the power of these two things that are available freely, and we can capture it for a long term. So that's the first point that I want to make. The second point is, if you're going to buy or invest in carbon credits, please ask your carbon capture provider, where are you going to park my carbon? Where is it that you're going to store it? It has to be buried deep, otherwise it makes no sense. If you leave it on the surface, like I said, it's going to decompose or it's going to catch fire and it goes back again. It has to go to the bottom of the earth. It has to go to the place where it's going to start mineralizing. That means it becomes from carbon dioxide to something else. It becomes a carbonate, it becomes chalk, it becomes gypsum, whatever it becomes a mineral where it gets locked forever. And finally, I think we need to look at how do we want to protect things like the Sahara? How do we want to protect Ganga? Our focus is setting up a Miyawaki forest in our backyard and we think we've done enough. No, it's not. In fact, you're doing more harm than good. You need to look at how can you take care of one landscape, Sundarbans, the Ganga, the Western Himalayas, the Thar Desert, you know. If we don't look at climate through the lens of landscapes, we are making a big mistake. We are only doing patchwork, and that's not going to work. Thank you so much. I hope this was useful.